Hello everyone. In this session, we are going to do all the questions of exercise 21B of the chapter Trigonometrical Identities from the textbook Concise Mathematics by Selina Publications for class 10. In case you want to refer to the answers of exercise 21A, the link is getting displayed on the screen right now. So now let's begin with the first question. The LHS of question first is given as cos A divided by 1 minus tan A plus sin A divided by 1 minus cot A. Now we will convert the tan A and cot A in the form of sin and cos. So we can write it as cos A divided by 1 minus sin A divided by cos A plus sin A divided by 1 minus cos A divided by sin A. This is because tan A is equal to sin A divided by cos A and cot A is equal to cos A divided by sin A. Now we will take the LCM here. The LCM is cos A. Cos A will get multiplied with 1 over here. This will give us cos A minus sin A and the numerator will be cos A. Similarly, we will get sin A divided by sin A minus cos A divided by sin A. Now, this cos A will get shifted to the numerator and will get multiplied. So, this will form cos square A divided by cos A minus sin A plus this sin A will get shifted in the numerator again and this will get multiplied. So, this will give us sin square A divided by sin A minus cos A. To make the denominator same, we will take the minus sign common from this denominator. So, this will become cos square A divided by cos A minus sin A minus, since we are taking the negative sign common here. So, this will become sin square A divided by cos A minus sin A. Now, we will take the denominator here which is common, that is cos A minus sin A, and the numerator now becomes cos square A minus sin square A. Cos square A minus sin square A is of the form A square minus B square. So, we will apply the formula. This will give us cos A plus sin A into cos A minus sin A. This is by the formula, since A square minus B square is equal to A plus B into A minus B. Now, cos A minus sin A, cos A minus sin A will get cancelled out and we are left with cos A plus sin A, which is sin A plus cos A and which is equal to the RHS, and hence we have proved that the left hand side is equal to the right hand side. In the second question, the LHS is given as cos cube A plus sin cube A divided by cos A plus sin A plus cos cube A minus sin cube A divided by cos A minus sin A. Here we can apply the formula of A cube plus B cube in the numerator, which will give us cos A plus sin A into cos square A minus cos A into sin A plus sin square A, and this will be divided by the denominator, that is cos A plus sin A. Similarly, we will apply the formula of A cube minus B cube here. This will become cos A minus sin A into cos square A plus cos A into sin A plus sin square A divided by cos A minus sin A. The formulae used here are A cube plus B cube is equal to A plus B into A square minus AB plus B square, and A cube minus B cube is equal to A minus B into A square plus AB plus B square. Now we can cancel out cos A plus sin A in the numerator and denominator. Similarly, we can cancel out cos A minus sin A in the numerator and denominator. So we are left here with cos square A minus cos A sin A plus sin square A, and from the second expression we will get cos square A plus cos A sin A plus sin square A. Now minus cos A sin A plus cos A sin A will get cancelled out, and we know by the trigonometrical identities that cos square A plus sin square A is equal to 1. So we will take 2 common here. So this is equal to 1 and 2 into 1 is equal to 2. This is by the trigonometric identity that cos square A plus sin square A is equal to 1. And 2 here is the RHS, and hence we have proved that the left hand side is equal to the right hand side. In the question number 3, the LHS is given as tan A divided by 1 minus cot A plus cot A divided by 1 minus tan A. Here we will convert the cot A terms in the form of tan A. So it can be written as tan A divided by 1 minus 1 upon tan A. And the numerator here can be written as 1 upon tan A divided by 1 minus tan A. This is because cot A is the reciprocal of tan A. Now we will take the LCM here. So this will become tan A divided by tan A minus 1 divided by tan A. And this will become 1 upon tan A, and this denominator will get multiplied with tan A. Now the tan A here can be shifted to the numerator. So this will become tan square A divided by tan A minus 1, and from this bracket we will take minus sign common. So this will become minus 1 divided by tan A, and the bracket now can be written as tan A minus 1. Here we can find out the LCM, which is equal to tan A into tan A minus 1. So the numerator here will get multiplied with tan A, which will give us tan cube A, and the numerator here will be 1. Now the numerator here can be written in the form of A cube minus B cube. So this will lead to the expansion, which is equal to tan A minus 1 into tan square A plus 1 plus tan A, and the denominator is still tan A divided by tan A minus 1. The formula that we have applied in the numerator here for A cube minus B cube is A minus B into A square plus AB plus B square. So tan A minus 1 will get cancelled out, and here we know that tan square A plus 1 is equal to sec square A by the trigonometric identity. So it can be written as sec square A plus tan A divided by this tan A. Now we will again change everything here in the form of sine and cos. So this will become 1 divided by cos square A plus sine A divided by cos A divided by sine A upon cos A. So 1 divided by cos square A divided by sin A cos A will be equal to 1 upon sin A into cos A, and sin A divided by cos A divided by sin A by cos A will just give us 1. Now this can be written as sec A into cosec A plus 1, which is equal to the RHS. The ratio here can be written in the form of sec A into cosec A, because 1 divided by sin A is equal to cosec A and 1 divided by cos A is equal to sec A. So we have used the relationship here, and hence the RHS is now equal to sec A into cosec A plus 1, and hence we have proved that the LHS is equal to the RHS. In the question number 4, the left hand side is given as tan A plus 1 divided by cos A whole square plus tan A minus 1 by cos A whole square. Now we can write tan A here in the form of sin A and cos A. This is because tan A is equal to sin A divided by cos A. Now we can write the numerator here as sin A plus 1 whole square, and the denominator will become cos square A. Similarly, the numerator here will become sin A minus 1 whole square, and the denominator will become cos square A. Now we can take the denominator as common, and the numerator here can be expanded with the form of A plus B whole square. So this will become sin square A plus 1 plus 2 sin A plus sin square A plus 1 minus 2 sin A. We are using the formula of A plus B whole square here. This is A square plus B square plus 2AB. Now 2 sin A minus 2 sin A will get cancelled out, and we are left here with 2 sin square A plus 2 divided by cos square A. We can take 2 common. This will become 1 plus sin square A, and the denominator cos square A can be written in the form of sin square A as 1 minus sin square A, since according to the trigonometric identity sin square A plus cos square A is equal to 1. Therefore, sin square A is equal to 1 minus cos square A, and cos square A is equal to 1 minus sin square A, which we have used over here. And this is equal to the RHS, and hence we have proved that the left hand side is equal to the right hand side. In the part 5, the LHS is given as 2 sin square A plus cos raised to 4A. Now we can write cos raised to 4A as cos square A whole square. This can be further written as 1 minus sin square A whole square, since according to the trigonometric identity sin square A plus cos square A is equal to 1. Therefore, cos square A is equal to 1 minus sin square A. Now we will expand it. So this will become 2 sin square A plus, here we are applying the formula of A minus B whole square. So this will be 1 square, which is 1, plus square of sin square A will be sin raised to 4A minus 2AB, which is equal to 2 sin square A. Now 2 sin square A minus 2 sin square A will get cancelled out. This will give us 1 plus sine 4a, and which is equal to the RHS, and hence we have proved that the left hand side is equal to the right hand side. In the part 6, the LHS is given as sine a minus sine b divided by cos a plus cos b plus cos a minus cos b divided by sine a plus sine b. Here we will find out the LCM by multiplication. So this will become cos a plus cos b into sine a plus sine b. The numerators will get cross multiplied, which will be of the form a minus b into a plus b. So this can be written as sine square a minus sine square b. Similarly, this is of the form a minus b into a plus b, which will give us cos square a minus cos square b. The formula used here is a plus b into a minus b is equal to a square minus b square. Now, sine square a plus cos square a is equal to 1, and sine square b plus cos square b is equal to 1. But here we have a negative sign, so this will become minus 1. This is divided by cos a plus cos b into sine a plus sine b. The numerator here will be equal to 0, and this will give us the answer as RHS is equal to LHS, and hence we have proved. In the part 7, the LHS is given as cosec a minus sine a into sec a minus cos a. Here we will convert cosec and sec in the form of sine and cos respectively. So this will become 1 divided by sine a minus sine a into 1 divided by cos a minus cos a. This is because cosec a is equal to 1 upon sine a and sec a is equal to 1 upon cos a. Now we will take the LCM here. So this will become sine a, and the numerator will become 1 minus sine square a. Similarly, the numerator will become 1 minus cos square a divided by cos a. Now 1 minus sine square a is equal to cos square a, and 1 minus cos square a is equal to sine square a. This is by the trigonometric identity that sine square a plus cos square a is equal to 1. Therefore, 1 minus sine square a is equal to cos square a, and 1 minus cos square a is equal to sine square a. So sine a will get cancelled out, cos a will get cancelled out, and we are left with sine a into cos a. Now here in this question we will mark it as a, and we will start now with the RHS, which is given as 1 upon tan a plus cot a. We will convert tan and cot in the form of sine and cos. So this can be written as 1 divided by sine a divided by cos a plus cos a divided by sine a. This is because tan a is equal to sine a upon cos a, and cot a is equal to cos a upon sine a. Now we will take the LCM. This will become sine a cos a, which will eventually move to the numerator, and the denominator will become sine square a plus cos square a. Sine square a plus cos square a is equal to 1 according to the trigonometric identity. So we are left with sine a into cos a in the numerator. Now this we are going to consider as b, Now you can see that the LHS was also equal to sin A into cos A, and the RHS is also equal to sin A into cos A, which means that the LHS is equal to RHS, which we are concluding from A and B. Therefore, we have proved that cosec A minus sin A into sec A minus cos A is equal to 1 divided by tan A plus cot A. So, this is proved. In the part 8, the LHS is given as 1 plus tan A into tan B whole square plus tan A minus tan B whole square. So, we will apply the formula of A plus B whole square, and here we will apply the formula of A minus B whole square. So, this will become 1 plus tan square A into tan square B plus 2 tan A into tan B, and this will become plus tan square A plus tan square B minus 2 tan A into tan B. We have applied the formula A plus B whole square, which is equal to A square plus B square plus 2AB, and A minus B whole square, which is equal to A square plus B square minus 2AB. 2 tan A into tan B minus 2 tan A into tan B will get cancelled out here. Now this will give us 1 plus tan square A plus tan square B plus tan square A into tan square B. Now we know from the trigonometric identity that 1 plus tan square A is equal to sec square A. So this will be written as sec square A plus tan square B can be taken out common from the last two terms. So this will become 1 plus tan square A. Since 1 plus tan square A is equal to sec square A according to the trigonometric identity. Now this can be written as sec square A plus tan square B. 1 plus tan square A here again can be written as sec square A. Again now we can take sec square A common from both the terms. So this will become 1 plus tan square B, and this can be written as sec square B now. This is equal to the RHS, and hence we have proved. In the question number 1, part 9, the LHS is given as 1 divided by cos A plus sin A minus 1 plus 1 divided by cos A plus sin A plus 1. If you will closely observe here, we can group cos A plus sin A in a bracket in both the terms. So now when we will find out the LCM, this will become of the form A minus B into A plus B. So this will give us the denominator of the form A square minus B square, which is equal to cos A plus sin A whole square minus 1 square, which is 1. And the numerator will be equal to cos A plus sin A plus 1 plus cos A plus sin A minus 1. The denominator here is, because of the formula, A minus B into A plus B is equal to A square minus B square. Plus 1 minus 1 will get cancelled out. So this will become 2 sin A plus cos A divided by, here we will apply the formula of A plus B whole square. So this will become cos square A plus sin square A plus 2 sin A cos A minus 1. Now we know that cos square A plus sin square A is equal to 1 by the trigonometric identity. So this will become 1 plus 2 sin A cos A minus 1. This is by the trigonometric identity that sin square theta plus cos square theta is equal to 1. Minus 1 plus 1 will get cancelled out. 2 and 2 will get cancelled out. So we are left with sin A plus cos A divided by sin A cos A. We can separate here the numerators. So this will become sin A divided by sin A into cos A plus cos A divided by sin A into cos A. Sin A will get cancelled out. Cos A will get cancelled out. This is 1 divided by cos A, which is equal to sec A, and this is 1 divided by sin A, which is equal to cosec A. This is because sec A is equal to 1 divided by cos A, and cosec A is equal to 1 divided by sin A. Now this is the RHS, so hence we have proved. In question 2, we are given that if x cos A plus y sin A is equal to m and x sin A minus y cos A is equal to n, then prove that x square plus y square is equal to m square plus n square. So here we will begin with the RHS, that is given as m square plus n square. So we will put the values now. M is given as x cos A plus y sin A. And n is given as x sin A minus y cos A. So we will apply the formula of a plus b whole square and a minus b whole square. This will become x square cos square A plus y square sin square A plus 2xy cos A sin A. The second bracket will become x square sin square A plus y square cos square A minus 2xy sin A cos A. This is by applying the formula a plus b whole square is equal to a square plus b square plus 2ab, and a minus b whole square is equal to a square plus b square minus 2ab. Now 2xy cos A sin A will be cancelled with minus 2xy sin A cos A. Now we are left with x square cos square A plus y square sin square A plus x square sin square A plus y square cos square A. Now here we will take x square common from this term and the third one. So it will become x square, and we will have sin square A plus cos square A in the bracket. Similarly, we will take y square common from these two terms. So it will become y square into sin square A plus cos square A in the bracket. Now we know by the trigonometric identity that sin square theta plus cos square theta is equal to 1. So this part would become 1. So this is x square into 1. Similarly, the bracket here will become 1. This is y square into 1. We are using the trigonometric identity sin square theta plus cos square theta is equal to 1. So this will become x square plus y square, which is equal to the LHS, and hence we have proved. In the question number 3, it is given if m is equal to a sec a plus b tan a and n is equal to a tan a plus b sec a, then we have to prove that m square minus n square is equal to a square minus b square. Here we will start with the left hand side, which is equal to m square minus n square, and now we will put the values. So the value of m is given as a sec a plus b tan a. So this would become square now. Similarly, we will put the value of n square, which is equal to a tan a plus b sec a whole square. Here we will apply the formula of a plus b whole square in both the brackets. So this would become a square sec square a plus b square tan square a plus 2ab sec a into tan a, and all the terms of the second bracket will become negative, and simultaneously we will apply the formula. So this will become minus a square tan square a minus b square sec square a and minus 2ab tan a into sec a. Here we have applied the formula of a plus b whole square, which is equal to a square plus b square plus 2ab. Now plus 2ab sec a into tan a will get cancelled with minus 2ab tan a into sec a. So we are left with now a square sec square a plus b square tan square a minus a square tan square a minus b square sec square a. Now we will take a square common from these two terms. It will become a square, and inside the bracket it will be sec square a minus tan square a. Similarly, we will take b square common from the other two terms. It will become b square into sec square a minus tan square a. Now sec square a minus tan square a is equal to 1 according to the trigonometric identity. So this will become a square into 1, that is equal to a square, and this will become b square into 1, which is equal to b square. We are applying the trigonometric identity here, that 1 plus tan square a is equal to sec square a. That means sec square a minus tan square a is equal to 1, which we have written here as 1. So this is equal to the right hand side, and hence we have proved. In question 4, we will again begin with the left hand side, which is equal to x square plus y square plus z square. The value of x, y, z are given in the question, so we will put the values now. So this will become r square sine square a into cos square b. Y square can be written as r square sine square a into sine square b, and z square can be written as r square cos square a. Now we can take r square sine square a common from the first two terms. So it will become r square sine square a, and in the bracket we will have cos square b plus sine square b. Now we know from the trigonometric identity that cos square theta plus sine square theta is equal to 1. So this part will become 1, and we are left with now r square sine square a plus r square cos square a. Now we will again take r square common from these two terms. It will become sine square a plus cos square a, which is again equal to 1. So this is equal to r square. The identity that we have used here is sine square theta plus cos square theta is equal to 1. This is the RHS, and hence we have proved. Let's now solve the question number 5. Here we have to show that n into m square minus 1 is equal to 2m. So we will start with the left hand side. The value of nm is given in the question, so we will use that. So we can write sec a plus cosec a into sin a plus cos a whole square minus 1. Now we will change sec a plus cosec a in terms of sin and cos. So sec a can be written as 1 upon cos a, and cosec a can be written as 1 upon sin a. Here we will apply the formula of a plus b whole square. So this will become sine square A plus cos square A plus 2 sine A cos A minus 1. Now we will take the LCM. This will become sine A into cos A. The numerator will become sine A plus cos A. Now we know that sine square A plus cos square A is equal to 1 by the trigonometric identity. So this will become 1, but it will get cancelled with minus 1. So we are left with 2 sine A into cos A here. The identity that we had used is sine square theta plus cos square theta is equal to 1. Now sine A cos A and sine A cos A will get cancelled out, and we are left with 2 into sine A plus cos A, and this is equal to m. Therefore we can replace it with m, and this is equal to the RHS, and hence we have proved that the left hand side is equal to the right hand side. In the question number 6, we will again begin with the left hand side, which is given as x square plus y square plus z square. The value of x, y and z are given in the question, so we will put that now. So this will become r square cos square A cos square B plus r square cos square A into sine square B plus r square sine square A. Now from the first two terms, we can take r square cos square A as common. So this will become cos square B plus sine square B. Now we know by the trigonometric identity that cos square theta plus sine square theta is equal to 1. So this will become 1. So we are left with r square cos square A plus r square sine square A now. Now again we will take r square common. So this will give us cos square A plus sine square A in the bracket. Now we again will use the identity that cos square theta plus sine square theta is equal to 1. So this is equal to r square, and which is also equal to the RHS, and hence we have proved. In question number 7, again we will begin with the left hand side, which is given as m square plus n square into cos square B. The values of m and n are given in the question, so we will put that now. So this will become cos square A divided by cos square B plus cos square A divided by sine square B into cos square B. Now we will cross multiply and also find the LCM. So the LCM is sine square B plus cos square B. The numerators will become cos square A into sine square B plus cos square A into cos square B. This cos square B will get cancelled now. Now we will take cos square A common from both the terms. So this will become cos square A into sine square B plus cos square B divided by sine square B. Now we know sine square theta plus cos square theta is equal to 1 according to the trigonometric identity. So we are left with cos square A upon sine square B, since sine square theta plus cos square theta is equal to 1. So here this can be written as cos A divided by sine B whole square, and which is equal to n. So we can replace it with n square now, which is also equal to the RHS, and hence we have proved that the left hand side is equal to the right hand side.